Let's take a look at this guy and see if we can figure out some of his signs or symptoms. This guy's just waiting for some third-degree burns. It can easily enough happen. So let's kind of look. Why is he thin in appearance, this guy with COPET? Well, think about this. For every second, every minute, every hour of every day, he's having that kind of purse-lip breathing. He's having to force that air out. He's having to use his accessory muscles. He's having to use his accessory muscles to force the air out. And because he's using muscles that he normally shouldn't be using for every breath, he's using a lot of energy. And that's going to burn calories. So yeah, smoking, getting emphysema is a good way to lose weight. Because, again, poor gas exchange, and he's having to use a lot of energy. He's easily fatigued. Frequent respiratory infections, we already said that. We mentioned that you have to use the accessory muscles to force that air out. Barrel chest, because he's hyperinflated. He's having difficulty to recoil. Elasticity is lost. Col pulmonale could lead to heart failure, which will involve the lungs more likely. You think that one out. Let's see, what else? Dyspnea is abnormal breathing. Yeah, remember, this would be what? Left-sided failure, because that's where it involves the lungs. The pulmonary system. Let's see, what else do we have here? Here's normal lungs. Let's take a look at a picture here. Here's your normal lungs. This is hyperinflated lungs. Think of a balloon. It's got some air in it. You squeeze it and squeeze it, see how it bulges out in places. But look at that color difference. Kind of pinkish. Still have a little bit of junk there. But here, black. So smokers, these are your lungs. I mean, it's not going to get better. Stop now so it doesn't keep progressing to eventually have a cancer. It's a horrible way of dying. You become so fatigued, you can't do anything, you become useless. My uncle died of emphysema, and he was pretty much, his body, he couldn't move. He was just absolutely fatigued. And his wife had to do everything for him. Go to the bathroom. I mean, everything. This is asthma being hyperinflated. It's kind of hard to really see it other than we got a bunch of adipose tissue. But asthma could cause hyperinflation. Here's a normal lung cross-section. Kind of look at the texture. Some of the bigger openings are maybe tertiary, quaternary bronchi. This may be a secondary. And look at this. Try to keep the shape, the size magnification the same. This is what I mean by hyperinflation. This is loss of lung elasticity. Some of the alveoli have been destroyed, and you can see how you got this airway trapping. This is definitely problematic. Now, if we go to page 6, do the second half, restrictive disorders. Now, what you're seeing here is tuberculosis, which is something that could cause a restrictive disorder. And look at all the junk here. In this case, the alveoli are all destroyed, and they're filled with microbes and white blood cells. So we don't even have a case of airway trapping. We have a case of where the air can't even get in. So imagine having all this white stuff in one region of the lungs, having it all in one region. So imagine, just for argument's sake, where I'm outlining, this whole region's all white. Well, can air get in there? No. So instead of having a lung where air can go in at any region, I've lost maybe a third of the lung. So I have 1/3 lung capacity, and this is a restricted disorder, so volume actually goes down. So I give you a problem and the numbers of going down, such as vital capacity, total lung capacity, functional residual capacity, and residual volume. If any of those numbers go down, it's a restricted disorder because you can't actually get the air in because it's filled with junk. Tuberculosis causes it. As you can see in this picture, polio is a problem with breathing. Your muscles are not working right, so your lungs just naturally don't want to expand. And if they don't want to expand because the diaphragm is not working, air can't get in, it's a restricted disorder. Lung cancer can do that too. And we'll talk about lung cancer in some detail. And next, let's see, probably page 7. We'll talk about lung cancer in detail. Okay, last two concepts, dead space and alveolar ventilation rate. Let's talk about dead space. Anatomical dead space is the volume of gas that never reaches your alveoli. Think about this. Take a breath. That last bit of breath, did it go to your lungs? No, it's probably either still in your nasal cavity or in your oral cavity, maybe made it into your pharynx. So any gas that's in the conducting zone, not the alveoli, but in the conducting zone, is considered dead space because it does not do gas exchange, and it adds up to be around 150 mils. Alveolar or physiological dead space is where the alveoli have been destroyed or are non-functioning. So obviously if they're non-functioning, if they're destroyed, you're not doing gas exchange. And total gas exchange, or dead space, is just anatomical dead space plus the physiological dead space. Now, anatomical, we know what its value is. The other one can vary depending upon what's going wrong. Okay, now we're going to use this definition to figure out alveolar ventilation rate. Okay? With AVR, we have this formula, breaths per minute times tidal volume minus dead space. And does this at all look familiar, like something that we have discussed before? It should look like cardiac output, because isn't cardiac output beats per minute times parentheses EDV minus ESV? So this is just cardiac output applied to the breathing system, so it's a rate of breathing. Volume of air move with each breath over a minute's period. So just like cardiac output, we don't want it being 0. We don't want AVR being 0. The bigger the cardiac output, the better off you are. The greater the AVR, the better off you are. Okay? So we have a couple of cases. We have a case with 20 breaths per minute, not beats per minute, but 20 breaths per minute with a 500 mils tidal volume and 150 mil dead space, and one where you have 60 breaths per minute with 500 mils tidal volume and 450 mil dead space. I'll give you a minute to work it out, and I'll get back with you. So hopefully for the first one, I'm doing my calculator right now, you got 7,000, and for the second one, you got 3,000. So let's see, what can we learn from that? 7,000 versus 3,000. So even though, what's the difference between the two? In the second case, I'm breathing faster, but by a factor of 3 times 20, but then I increase my dead space by a factor of 3, 150 versus 450. So even though I'm breathing faster, with a greater dead space, that's useless. So we're going to try to realize that a good couple of deep breaths is way better than many shallow breaths. Because really, the second case, when you're at 60 breaths per minute with a huge dead space, you're really barely breathing. You're like going like this. The air is barely entering you. So doing many shallow breaths, the air just doesn't get to you. It's useless. So when you want to have really good gas exchange, a few good deep breaths outweighs many shallow breaths. And what I want you to do is kind of, maybe for a couple examples, make up some numbers, throw it in there, and see how it works out. Okay?